Assalamu alaikum. Welcome to lecture 26 of data mining. So today we will continue with our discussion on time series analysis, which we started last time. And we will be discussing forecasting and motif detection today. And maybe also start a bit about clustering. So essentially, this is the last week of the semester. We have this lecture and the next lecture on Thursday. So I don't think so I will be able to start any new content beyond that. So these two lectures would then conclude the semester of data mining that we have discussed. So so then we will have the break, and then we have the exam after the break in May. So today, of course, as I said, we will continue our discussion on time series analysis. So time series, as we mentioned last time, is a contextual data type. So we have behavioral attributes and you have contextual or we have contextual attributes. So the contextual attribute in the case of time series is time, and the behavioral attribute could be anything which is recorded at a particular point in time. So usually it's a scalar, in which case it's called univariate. If it is a vector, then it will be multivariate. And it could be other data type as well, but these are the two most common, univariate and multivariate. So let's get started then. Okay. Okay. So we had talked about various time series pre-processing steps and tasks last time. We had also started talking about forecasting. So let's start with that today. So time series forecasting. So this is one of the most popular applications for time series data, in which you are trying to predict the value of the behavioral attribute at a future time. And we have various applications of this in different domains. So you can think of retail price prediction, stock price prediction, weather forecasting, wherever, and of course, you have examples in the medical domain as well. So medical condition prediction in the future. So all of that would fall under time series forecasting. So, so the traditional techniques in time series forecasting are autoregressive modeling. Then we have autoregressive moving average modeling. And then we have what is known as autoregressive integrated moving average modeling. So all of these, of course, are based on some model of the time series data. So an autoregressive model considers that considers the correlation between the values at different time stamps. So if we consider the values x, for example, so x1 is the value at time 1, so x2, x3, and so on. So the correlation between x3 and x2, x3 and x1, x2 and x1, so this is exploited in developing the autoregressive model. And in general, since we are talking about a particular phenomena that is generating this time series, there is going to be positive correlation between two values that are recorded at close time intervals. So this is, of course, you can say the law of nature. So if you think of anything like temperature recording, so temperature recording, let's say today is 25, so tomorrow is not going to be 45, and the next day is not going to be -10. It's going to be related to 45, for example, or it's going to be related to 25. So though corresponding values 25, 26, 25, 28, so these values would be close to each other, and as such there would be strong correlation between values that are close together. But if you Go several months later, maybe these values are recorded in March, and then you go into May, then you have 40, 41, 40, 42, and so on. So the correlation would decrease as the time span between values increases for most natural phenomena, natural as well as physical phenomena. Okay. So this naturally leads us to the idea, of course, if there is a correlation, then that would help us predict the next value. So we would thus like to include a window of values which are reasonably well correlated in our prediction model. So that basically is auto-regressive prediction model. So essentially, so we are predicting xt. So this is essentially going to be the sigma operator sum over I is equal to 1 to, let's say, p time steps. B, this is a parameter. I think last time I gave a parameter of w. So bi into, then we have x t minus I. And usually we'll also have a parameter at 0, the bias parameter. So this is essentially the auto-regressive model, and we have the parameters b's as the parameters. And the window of time that we are considering in this auto-regressive model is p. So as such, this is also called an auto-regressive p model. So we are considering p time steps for building the auto-regressive model. So this model exploits, as I said, the correlation between values that are close to each other, and we thus consider a window of values, p windows of p values in that window, and hopefully those p values are all have some correlation with the next value. Obviously, if p is very large, then the correlation would decrease and you tend to have independent values. By the way, this correlation can be both positive and negative. So both are considered. As long as the correlation is strong, either in the positive side or the negative side, we will consider it in the model because it will help us predict the next value. So, okay, so this is the model. How do you actually find these parameters? This is actually the standard learning problem. So learning, so we want to learn the parameters. So these are the parameters. So for this, we typically need data, and the data, of course, is available within the time series. So there isn't any need for external supervision of the data. Let's say you have okay. So we have data. So data is your time series X, of course. So I is equal to 1 to n. And of course, for building this parameter, building this model, you need the parameter P as well, the window length. So of course, you will fix that at start. And then let's say the predicted value, let me call that X prime T. So this is the predicted value. So the equation that I wrote there would be for the predicted value. So a predicted value. So, and you have the data set X, and for each X, you have the predicted value for some B's. The goal is, of course, to minimize the difference between the two, and we can use various loss functions. The most common loss function is the root mean squared error, or even sometimes sum of squared error. That should be fine. I think sum of squared error is better because it has better convergence properties. So what is the sum of squared error? Simply you are summing over the data. Yeah, I is equal to 1 to n, and you're simply taking the squared difference between the two. So x I minus x prime I square. So this is the objective function or the loss function which you minimize. Of course, x prime is given by that formula, which is a parametric model, which has the b's as parameters. So minimization of this would lead to the final values or the optimal values of b. So this is called the least square formulation for this regression problem. So we are minimizing the sum of squared errors. So that's the least minimization, least square. So after minimizing this, you get the parameters b, which you can say b stars. So all the optimal parameters. So once you have those parameters, you can use it for. So once you have this b star, then you can use it for making predictions. So you have, of course, the sum over I is equal to 1 to p to b star I into x t minus plus, of course, b naught. So when you put, of course, b naught is also star. Okay. So once you put in the values for x's, you can get the value for x at the next time step, which is xt. So this is the autoregressive model. So somewhat more complicated models from the traditional approaches are the ARMA. So ARMA is autoregressive moving average. Auto-regressive moving average. So this has two sets of parameters. In other words, it assumes that the prediction for the next value is dependent on correlation, as we did for autoregressive, as well as it is dependent on the average that is moving from the previous time step. So the average of the previous time steps would help us predict the next value. So that's the main idea behind this. So both of these things are used together. So that's why this is called the ARMA model. So essentially, the model would thus become x prime t is equal to, you have a summation over I is equal to 1 to p. This is the AR standard AR model, b I into x t minus I. So this is AR model. Plus you have a second model, the moving average model, sum, a second summation over I is equal to 1 to q. So this is the window, you can say, for the moving average that can be different from p. Okay, the moving average window. And then we have another set of parameters. इस parameter को a कह देते हैं हम, ai into the difference in the values of the predicted value and the moving average. So that I can call it, let's say, epsilon t minus I. Plus, of course, a global mean, plus a global average of the entire time series. Okay. So C, of course, can be computed upfront. Of course, इसमें मैंने B नॉट और A नॉट नहीं लिखे, वो भी आपने डालने. Of course, A नॉट और B नॉट डालेंगे तो वो A नॉट C बन जाएगा. जब आप उसको पैरामीटर लर्न करें, exactly वो C आएगा. But खैर, I've written it, I've used the notation in the book as much as possible. So by the way, this is from the book by Agarwal, chapter 14. I think I need to upload the chapter. Chapter भी upload नहीं किया मैंने. I'll do that. So A naught and B naught are also parameters, but if you learn them, usually जो A naught होगा वो C होगा. C is what? C is the average value of time series. ठीक है? So, okay, what is epsilon, by the way? So epsilon is actually the difference between actual value and the moving average value at a particular time t or I. So this is epsilon. So the actual value, since we won't, so to find the difference, of course, actual value and the predicted value, you need the predicted value, right? Very difference मिलेगा ना आपको. So in a way, this equation thus becomes coupled. Right hand side में आपका x prime की जरूरत पड़ रही है. In other words, you need, if you want to compute epsilon, you need x prime. X prime of course is on the left hand side, so this equation is coupled. So इसको iteratively solve किया जाता है typically. Simple एक कह लें कि the simple least square solution जो ऊपर वाले का था वो नहीं हो सकता इसमें. ठीक है. But the main idea that I want to convey is we are modeling both correlation and moving average, and the hypothesis that correlation helps us predict the next value. The moving average that comes from the previous values also help us predict the next value. And of course, we are attaching parameters with them and using them to predict the next value. So इसी तरह एक next level आ जाता है, which is, you might have heard about, is called, by the way, ये जो ऊपर वाला model है, this is called ARMA P comma Q model. So P is the length of the window for AR, autoregressive, and Q is the length of the window for moving average. And then we also have what is ARIMA model, ARIMA model. So इसमें D एक parameter आ जाएगा, P आ जाएगा, Q आ जाएगा. So I basically stands for integrated, autoregressive integrated moving average, which basically says that differencing हम ले रहे हैं. So in other words, we're saying that we can also predict the next value based on the difference of values in the observed values. For example, very simple. So let's say आपके पास एक straight line है यूं करके. So obviously, if this is a straight line, if you take the difference of every value from the next value, if you plot and take the difference in, then you plot, you'll get a straight horizontal line. Okay. So once you have a horizontal line, obviously you can predict the next value as the same as the previous value. So these are all techniques that help us predict the next value based on the observations of the previous values. So differencing से आपकी line prediction better हो जाती है, then you can do that. By the way, all of these techniques are techniques for making your data set stationary. So the idea of stationarity is part of this whole idea. Okay. So for example, ये आपके पास x1 था इधर, फिर x2 उससे ज्यादा था, x3 था, तो आप x2 minus x1 plot करेंगे, x3 minus x2 plot करेंगे. All of these values will be the same, 2, 2, 2. So as I said, let's say आपके पास 3, 5, 7 है. What's happening here? Okay. So 3, 5, 7, 5 minus 3 is 2, 7 minus 5 is also 2, so you get a horizontal line. Okay. So differencing sometimes can also make your data set more towards stationarity and help you improve prediction. So the ARIMA model basically also includes a third parametric model, which is based on differencing. Okay? So usually ये single or two steps पीछे हो सकता है. तो again, the model that you get is very similar. Sum I is equal to 1 P. This is for the ARIMA. You have BI into X T minus I. Then you have the other for moving average. I is equal to 1 Q. Then we have AI, let's say, into X T minus I. And then the third, of course, is for differencing. Actually, वो XI नहीं होगा, वो epsilon होगा. And then let's say we have some other parameter Ci into the difference of the current value with the predicted value. So I can call this something else, let's say mu T minus I. So of course you can take the difference for usually a few steps. D generally छोटा होता है, 1 या 2 maximum. वो ज़्यादा हम नहीं करते इसको. First order, second order तक maximum लेके जाते हैं. So this would be the ARIMA model. And again, this is coupled and you have to solve it using an iterative approach. Okay, so this was more or less some of the traditional techniques, and they are still used, but nowadays, most of the time series forecasting is done using neural networks. So, of course, we can't cover the whole neural networks in just a few minutes in lecture, so I'm just going to give you an overview. So this is, for example, covered in more detail in the NLP course, where we discuss sequential models in the neural network domain. So basically, we want to use sequential, or I should say recurrent in general. So sequential neural networks are now commonly used for time series forecasting. And recurrent neural networks, we have the standard RNN or standard recurrent neural network. And then we have some gated recurrent neural networks, which we call the gated recurrent unit. Or we also have another one, which is called a long short-term memory network. And more recently, which we have recurrent a sequential model, which we call a transformer. So all of these models can be used for time series forecasting, and they have proven to be quite effective as well as accurate, as opposed to the parametric models that we are talking about earlier using ARIMA and ARMA and so on. So let me just give you an idea how this works. So let's say if you talk about a standard RNN, recurrent neural network. So what happens in the standard recurrent neural network, you basically are inputting each value. So you input X1, then you input X2 into the network. Each of this is transformed through some nonlinear operations and some parameters. And the output of the previous input X1 is also fed in to the next input. In other words, the context is always maintained. And the parameters would be able to track which value to emphasize, which value not to emphasize. So remember when we were designing using ARMA and ARIMA and AR, we were explicitly modeling, like we wanted differencing, we wanted moving averages, we wanted correlation. So all of this stuff is actually learned automatically in neural networks automatically. So through the parameters, these behaviors are going to be learned automatically. You don't need to do explicit modeling of the data. So that's the biggest strength of neural networks. It can learn the various behaviors between different time values automatically. So once you have inputted, of course, actually there are different flavors. The whole thing is we can't discuss this in reasonable detail in a short time. So I think it's sufficient to say that you can use recurrent neural networks as well as its variants like transformer to make decent and fairly useful, accurate predictions for time series. One other advantage of using neural networks is that you can handle univariate and multivariate time series in a seamless manner, in a similar manner. So unlike when we discussed ARMA and ARIMA and AR, we were talking about a scalar behavioral attribute X. X was not a vector. So X was not a vector, and we were able to, we just consider X to be a scalar, and we use those models to predict a scalar. While in a neural network, you can easily extend it to vectors where X is multiple things that we recorded at a particular point in time. So in other words, so if you have X as a vector, so X can be a vector, right? So you can input, let's say if X is of length, let's say 30, you 30 distinct values. So your RNN would have 30 inputs. So at each time step, 30 inputs will go into the network. So the first time step, 30 inputs will go into the network. Second time step, 30 inputs will go into the network. And the RNN would be able to track the correlation between the values at different time steps, as well as the values within the vector at a particular time step. So it can model those behaviors, whether it's correlation, it is differencing or moving average or other complex behavior. It will be able to learn that automatically. And this X can contain information that is, you can say, yeah, I think that's application dependent, but it's information recorded at a particular time step. It could be anything. It could be even the name of a person, which usually is not considered to be time dependent, but it can still be inputted into the value X. So given these inputs into the neural network, you get the corresponding outputs, which will be the prediction for the next time step. Okay. So you can use some off-the-shelf tools for these models to train your recurrent neural network or transformer or LSTM and GRU. So many TensorFlow, for example, would have implementations of these. You can use them for your time series prediction. And as I said, in practice nowadays, mostly people use these models, not those ARMA and ARIMA and so on. All right. Okay, so now let's move on. So now let's talk about uh, motif detection. Or detection, or you can say, yeah, that's detection is fine. So what exactly, first of all, is a motif? So motif, of course, is an English word, is a occurring pattern. So any pattern that is frequently occurring is a motif. And since our context here is time series, our pattern would be some, you can say, behavior over time, over a small time window. And we will like thus to find frequently occurring such patterns in our data set. So there are various different settings in which this can be done. So let's discuss those settings. So let's say you have single time series. So if you have a single time series, so you have just one long time series. It could be multivariate, it could be univariate, but let's just consider univariate for the time being. Let's say temperature के आपके पास recordings हैं over the previous, let's say 3 months, daily temperature over the previous 3 months. So we now want to find motifs in this. What does that mean? We want to find some specific behavior. Let's say 3 day का behavior है कि first day पे low है, second day पे high है, third day पे फिर low, kind of like a peak. So let's say this is a small motif. So we want to detect whether this motif occurs in the data set. That's one thing. And of course, motif is something that occurs frequently. So we would like to find some motif, something that occurs frequently in this single stream. So maybe after analysis, we find that it's a pattern like low, high, high, low is something that occurs more frequently. Frequently would, of course, based on ratios, depending on your length of the time series. So if this is the most commonly occurring pattern in this time series, then we say that this is a top motif in this data set, single time series. So what is the pattern? You can even actually give values. So let's say values could be, let's say 20, 25, 28, and 22. So let's say this value or values that are close to this are most frequently occurring in a single time series. And let's say this time series is for temperature. So this would be for a single time series. So let's say if you have multiple time series. So meaning that you have temperature recordings for, let's say, 30 places in DHA over the same time period. So now in this case, motif detection would be, I want to find a pattern which occurs frequently in all those 30 time series, meaning that which pattern occurs in all of those patterns. So that would be the pattern that has a frequency of 30 or 30 or 100%. So if it occurs in all those 30 patterns, then that would be the most frequent motif. That would be the top motif. But of course, we are finding, we would like to find lower ones as well. Okay, so that would be across multiple time series. We are not looking at a single time series. We are looking at multiple time series and a motif, a pattern that occurs in those time series. And other variations of applications are maybe you want to find contiguous patterns. Contiguous patterns, and the flip is non-contiguous. So meaning that, are you considering motifs that are contiguous or non-contiguous? So non-contiguous motifs would have gaps, and those gaps could be of arbitrary length. So let's say आपका जो pattern है कि let's say शुरू में ऊपर है और बाद में नीचे है, but बीच में आप कोई भी gap रख सकते हैं. So this pattern up and then down, irrespective of the gap between them, would be non-contiguous. So if we want patterns that are up and down without any gap, that would be contiguous. So motif detection या motif analysis में ये एक difference भी आता. Most of the analysis would be of contiguous nature. And then you can have also another dimension of analysis or variation in analysis is what we call as multiscale. So multi-scale motif analysis would mean that you're finding patterns at different levels of granularity. So let's say, again, considering the issue of temperature. So you're recording temperatures daily, let's say. But while you're finding motifs, you're also finding motifs at the level of days, as well as at the level of weeks, as well as the level of months. So what are the patterns over months? What are the patterns over weeks? What are the patterns over days? So that would be multi-scale. And of course, single scale would have a fixed scale, whatever you specify. That it could be daily, it could be weekly, and so on. All right, so let's move on. One quick thing. Motif detection is the word commonly used when you are analyzing time series that consist of behavioral attributes or that consist of numeric behavioral attributes. If your behavioral attributes are discrete, motif analysis essentially becomes your sequential pattern mining. So if you convert your time series to discrete values, in other words, you're converting it to sequences, then motif analysis essentially becomes sequential pattern mining or sequential pattern analysis. And finding patterns in sequences, in multiple sequences, for example, could be done through GSP, which we studied earlier on, generalized sequential pattern. And you can also find patterns within a single sequence as well. Of course, we did not study that explicitly in the course, but it's very similar to GSP as well. Okay. So if you convert your data set to discrete values, then you have, I would say, more techniques for motif analysis than if you keep it in continuous values. So for example, non-contiguous sequential pattern analysis is much easier or more developed when you are dealing with sequences than when you're dealing with continuous time series. So this is something that you can consider. You can convert your data to discrete values and then apply the techniques that we studied for discrete analysis, pattern mining, as well as sequential pattern mining. Okay. So now let's quickly look at one technique which is applied to continuous time series, which is called basically is I don't forgotten the exact name, distance-based uh, motif analysis. So essentially, here we are matching the motif with the time series using a distance function or a similarity function. And we mentioned distance and similarity functions in the last lecture for time series. Either you typically use Euclidean distance if the two time series are of the same length. You can use Euclidean distance or its variant like Manhattan distance if you like. And if the two time series are not of the same length, then we typically use dynamic time warping, DTW, which basically adjusts the scales of the two time series and then does the Euclidean distance computation. So both of those can be used to find distances between time series. So in the case of motifs, so what exactly is a motif? So motif itself is a time series. Let's say it's a S, so S1 to SW, some window length. Okay. And of course, your original time series is X, X1 to XN. Okay. So original time series is X and a motif is S1 to SW. Of course, for this approach, you will have to specify W. कि कितनी विंडो को आपने कंसिडर करना है एज ए मोटिव. It's a parameter of this approach. And then essentially what happens is basically nested loop search आपको करनी पड़ती है. Essentially क्या हो रहा है, basically आप start करते हैं from start x1 to xw. So w थी ना width आपकी motive की, तो ये आपने ले लिया and you consider this to be a candidate motive, first motive. Of course से पहले कोई और motive बन नहीं सकता, ठीक है. And then you move the window forward one, and once you move the window forward, you compute the distance of this motive with that window. Of course, ये थोड़ा सा difference था, तो the distance would be quite low. So we also sometimes have to keep a parameter कि कितना हमने आगे jump करना है. So usually single jump से काफी similarity आएगी, हम jump थोड़ा सा ज़्यादा करवाते हैं, maybe half of W. ठीक है. So we jump forward by half of W and then find how much this time sequence from x1 to xw matches that from x, let's say w10 था तो x5 से x15. And then we continue this session 10 to 20, 25 to 30. So whenever the match is less than some user specified threshold, remember this is distance, so distance should be less than some threshold. Then we say that this is a match and we record it. And we then record also, of course, all matches and count them कि कितने matches एक time series में हो रहे हैं. And we can do this for multiple. Of course, ये पहली हमने ली थी तो उसको हमने आगे भी पे move करना है, वो एक motive लेना है और फिर आपको content. So for example, so let me just take concrete example. Let's say 1 to n आपका let's say 100 है, let's say, ठीक है. ठीक है, और let's say w, let's say मेरे पास 20 है, ठीक है. So what would happen? तो पहले आप मोटिव जो कंसिडर करेंगे वो 1 to 20 का होगा, और ये आप चेक करेंगे ओवर द एंटायर सीक्वेंस. द अदर दैट विल चेक अगेन, लेट्स से जंपिंग हम हाफ की करते हैं तो 10 to 30 का करेंगे, फिर 20 to 40 का करेंगे एंड सो ऑन. सो नेस्टेड लूप होगा, ऊपर एक लूप चलेगा, अंदर लूप चलेगा. ऊपर हम लूप में हम मोटिव बनाएंगे, नीचे वाले लूप में हम मैचिंग करने की कोशिश करेंगे कहाँ वो मैच हो रहा है. मैच ऑफ कोर्स बेस्ड ऑन सम थ्रेशोल्ड, और जो मैच हो जाता है वी कीप ए काउंटर एंड एट द एंड ऑफ द डे वी रिटर्न द motives that has the maximum match or the top k matches. Actually we want to return the motives at the end of the day. So 0 to 20, 10 to 20 ये motives हैं. तो लेट्स से हमने एक ही मोटिव ढूंढना है, तो हमको फिर पता चलेगा कौन सा मोटिव है जो मोस्ट फ्रीक्वेंट है इसमें. सो मे बी इट इज लाइक 40 to 50. So that would be outputted if you want to just one motive. If you want the top k motive, maybe 40 to 50 10 दफा आ रहा था, और 10 to 20 लेट्स से 3 दफा आ रहा था, दो ही थे, उसके बाद सारे थोड़े थे, तो ये दो टॉप 2 हो जाएंगे. This is what you are getting at the end of the day. So what is required here? Of course, you just need the window. W is required as a parameter. The second thing that's required is, of course, some measure of similarity. If the two time series are of the same length, you can simply use Euclidean distance, which in this case is possible. If not, and you are also want to consider gaps, then you use DTW. And then you do a kind of nested loop analysis over the time series to find the motives. So just some, for example, there are some common recurring patterns in many applications. So if you talk about the retail sector, so there's several patterns that are well known. For example, seasonal patterns. So this is also true for weather. So for example, summer में weather हमेशा hot रहता है, winter में cold होता है. So these pattern will repeat. ठीक है? So if you allow the algorithm to find motifs, then this would be a motif that you find in weather pattern कि summer में थोड़ा सा पहले नीचे होगा फिर ऊपर जाएगा फिर नीचे आएगा, ठीक है. एंड ऑफ कोर्स सीजनल आपके बाइंग बिहेवियर्स में भी हो सकता है, फाइनेंशियल ट्रांजैक्शंस में भी हो सकता है, सो ऑन. So for example, in the case here in Pakistan, usually before Eid, you have a spike in buying. So this would repeat every year just before Eid. So these are seasonal patterns which could be discovered by motif analysis. So there could be other patterns as well. Periodic behaviors can arise because of various physical and natural phenomena. So stock markets के भी patterns हो सकते हैं. Maybe there are patterns associated with change in government. There are patterns associated with currency valuation and so on, devaluation and so on. So again, motif detection algorithms would hopefully find this without you explicitly determining whether there is seasonality in the data set or not. Okay, so this distance-based approach that I mentioned is for contiguous time series only, contiguous patterns only. It's not applicable to non-contiguous patterns. And so far we have discussed the scenario where we talked about one time series. If you had multiple time series, actually this can be done, you can extend it very similarly. So you can take a motif from one time series and then try to find whether it occurs in other time series or not. Okay, and then you have to repeat it for all. Again, this would be like a nested loop. You have to find all motifs from one time series and check in all the others. Then go to the next time series, find all motifs, check in all the others, and so on. So again, nested loop approach से आप ये निकाल सकते हैं. Of course, for multiple time series, as I mentioned before, if you convert it to discrete values, then maybe the GSP or prefix span algorithms might be much better. They can even find patterns which have gaps in them. Okay, so that was a bit about motifs. Of course, there are more advanced techniques here as well, but we won't be going into them. So let's talk about time series clustering. So remember at the start of this section or this chapter, I mentioned that most of the techniques in this section are very similar or almost identical to the techniques that we have already studied. The only difference is that we are shaping the problem accordingly because we are not dealing with time series, and based on particular application, we choose a particular technique that we have already studied to do the analysis. Okay. So for clustering, we have already studied a lot of clustering algorithm, but now we are talking about clustering time series. So in this case, there are two scenarios that are typically used. So one is online clustering of, you can say, multiple time series, or a single time series or single multivariate time series. ठीक है, so आपके पास, let's say, temperature recordings have for 30 positions in DHA, you can combine all those into one time series with 30 values, or you can also consider them to be 30 different time series. So it's the same thing. Okay. So here, this setting or this scenarios, we are trying to cluster them as the data comes in. So the clustering here is actually, so let's take the example of 30 temperature at 30 locations. location. Okay. So the clustering here is now the clustering of those 30 locations. कि कौन सी दो locations ऐसी हैं जो similar हैं, in this case with respect to temperature. ठीक है. So in other words, so मतलब आपके पास what's happening here? So you have multiple time series. ठीक है. So what we are trying to determine is कौन सी time lines हैं that are similar. So maybe at the end of the day, let's say मेरे पास time series है A. This is not writing properly, so let me just go there. So let's say those locations are A, B, and C, and so on. So at the end of the clustering or the clustering, what we would like to find is that A, B, or E एक group है, or let's say D, E, and F दूसरा group है, based on whether those values are similar to each other or not. ठीक है. So इसमें typically हम क्या करेंगे, we'll take a window of time. Let's say these recordings are daily recordings, so हम window ले लेंगे weekly window of 1 week. So when you say you have a window of 1 week, you now have data which is 30 by 7. ठीक है. 30 by 7 meaning that आपके पास 30 वो हैं locations हैं और 7 time periods हैं. And what we want to cluster is those 30. So you can consider those 7 time points as the features for these 30 locations. And then you can apply any of your standard clustering algorithm to do the clustering. So do you get this point? So 7 days जो बनेंगे वो आपके features हो जाएंगे. 30 of course वो आपके objects हैं which you want to determine कि A B के साथ जा रहा है या A D के साथ जा रहा है, and you can apply k-means or whatever algorithm that you have to do this. Of course, this would be incremental clustering using a window, but you can also apply birch. Birch जो हमने study किया था वो at each point पे वो cluster कर देता है, तो वो भी आप कर सकते हैं. ठीक है. Another approach, this is one approach. Another approach is based on actually correlation, which they call as online correlation clustering. And I wouldn't be able to go into detail of this, but the idea here is that, remember, we have 30 time series, 30 values coming from 30 locations. So what this approach does is finds the correlation of a particular time series with the other time series. So if two time series are strongly correlated, then they will fall in one cluster. In other words, कि यहाँ जो similarity measure है, it's based on correlation, not based on some other thing, but it's based on correlation. So if the values of one location is increasing and the values of other location are also increasing, and the third location are also increasing, so all of these three would come into one cluster. So this is the general idea. Algorithm is also quite easy, but I won't go into the details. So you'll find it implemented in some places where you have algorithms for time series analysis. So I mentioned two techniques. One technique is define a window and consider that window to be your set of features, and then you do the clustering using any algorithm that you are comfortable with, hierarchical clustering or partitional clustering. The other approach is consider those time series as, of course, time series, and then consider the relationship between two time series by their correlation. And then based on this, you do the clustering. So that was basically clustering of a multivariate time series or multiple time series, which is, you can say, over the same time period online, as I mentioned before, coming at the same time period. So the other setting in which clustering can be done is you already have a database of time series. So in this case, in the previous case, it was online. We are getting recording values over time. In this case, you have already recorded time series values. So maybe you have different ECGs, for example, for hundreds of patients. Okay. So it is already recorded. It's not, you can say, online. So in this case, you will now want to cluster all those time series. So let's say is for 100 patients. So we now like to cluster those ECGs and find those patients that are similar and find those patients that are dissimilar. Okay. So this is the second scenario. This scenario becomes very easy if all those time series are of the same length and you have the same number of points for each time series. Then you can use those points as we did for online case as features, and those 100 patients as objects. So कोई भी आप algorithm लगा लें, k-mean लगा लें, k-mean लगा लें, do the clustering. But if those ECGs are not of the same length or they don't have the same number of values, फिर आपको थोड़ा सा इसको tweaking करनी पड़ेगी. You typically would have to rely upon techniques like DTW, dynamic time warping, to match the shapes of the ECGs for different patients. Okay? So if the time series are of the same length and the same number of values, of course, you can apply k-means and whatever you like to do the clustering. If they are of different technique, then you can use the dynamic time warping approach to find the similarity, which basically stretches and contracts the time series so that they match according to shape. So this is also sometimes called shape clustering. So you have different time series in your database and you're clustering them based on their shape. So obviously two time series would belong to one group if their shape are the same. Well, when their shapes are the same, then their distance would be the least. So they will be most similar. Okay, so this is also called as a shape clustering. Sure. ठीक है. So इसके बाद I think there are a couple of more things left. One is outlier detection for time series. The other is classification. I think we can do this in the next lecture, which will probably be the last lecture of content for this course. And ठीक है, तो I think we'll stop here and we'll restart on Thursday, which will be the last lecture for this course. We will be finishing the discussion on time series, which is chapter 14 of the Agarwal book. ठीक है.